this episode, we would like to say that in the spirit of reconciliation, that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community. Welcome back to another episode of Spaghettification. I'm the Drunk Astronomer.
And I'm Astrophysics. Today we have with us Maddie Marshall. Maddie's currently a Plaskett Fellow at the National Research Council of Canada, Hertzberg Astronomy and Astrophysics Research Centre in Victoria, British Columbia. Before this, she completed her PhD at the University of Melbourne and the ARC Centre of Excellence for All-Sky Astrophysics in 3 Dimensions, Astro 3D. She studies galaxies and supermassive black holes in the early universe using computer simulations and space telescopes, and is leading a James Webb Space Telescope program to study the host galaxies of the first quasars, and is involved with several other exciting JWST projects studying the early universe. Welcome.
Hello.
So we have a few questions for you. So my first one is, and one that I think we've talked about before, you grew up in Tasmania before moving to Melbourne and then to Vancouver Island in Canada. What's so great about islands, Maddie?
Oh, islands are great. Get away from all the crowds. Nothing like being isolated.
It was useful for you in COVID, wasn't it?
Yes, yeah, it was. Yeah, no, I prefer small places. Mm-hmm. So yeah, so I'm living in Vancouver Island now, and it's very similar to Tassie for all of our Australian listeners who have been to Tassie. It's kind of like that, but a bit more Canadian, more bears and cougars.
We're not here to talk about Tasmania or Vancouver Island. We're here to talk about physics and astronomy. And the first question I have is, what got you into physics and astronomy?
So it's a good question. The usual answer I'm sure you get is, oh, I love looking at the sky and I always wanted to be an astronaut or whatever. Literally until my first year of university, had no intention or even real interest in astronomy. I just didn't really know anything about it. I actually went to university to become a math teacher, and that involved also taking physics classes and astronomy classes. And the more astronomy classes I did, the more I realized that was way better than math. I was like, what am I doing? I want to do this instead. So yeah, it was not a plan, but it's worked out really well.
Maths is boring.
Yeah.
and it's surprising how many astronomers and astrophysicists, not astronomers, but astrophysicists don't actually look through telescopes either. Visual telescopes. Yeah. There's so many of them. They're like, oh, I've never seen through a telescope. It's quite a common one. If you taken an interest in actually physically looking at the stars through scopes, or at galaxies and nebula, or are you another one of those computer scientists?
I'm a computer scientist. I have looked at telescopes a few times. Actually, I actually looked through one today for the first time in a very long time. We had a solar telescope set up, and I got to see lots of beautiful sunspots today. But no, I don't look through telescopes. My telescopes are all in space.
Yeah. It's pretty active, the sun, at the moment, that's for sure. A lot of the solar astronomers I know are very excited at the moment with everything going on.
Yeah, it certainly looked spotty. So not that I've got anything to compare it to.
Yep. Lots of spots. Apparently, they've all got numbers and information attached to them. Bugger if I know what they are, though.
Yeah. There's lots and lots of small spots at the moment, as opposed to just a few big ones. So, yeah, don't look at the sun though.
No,
please use a solar telescope.
So that sort of leads on to my next question. So you study black holes and galaxies that they live in. How do you study black holes when they're, black?
So weirdly enough, black holes are, some of them, actually the brightest objects in the universe, which makes no sense. But what we're seeing is not the black hole itself. So black holes, nothing can escape a black hole, even light. And so we can't see anything from there. But around supermassive black holes, an accretion disk can form. So this is if there's any gas or dust or material in the center of a galaxy where the supermassive black hole sits, it will gravitationally form a disk around the black hole. And then because of the extreme gravity of the black hole, to be stable, that disk has to spin extremely fast. And so anything that's fast is hot, and anything that's hot is bright in terms of emitting radiation. And so these disks are the brightest objects in the universe. And so when we see a disk, one of these accretion disks around a supermassive black hole, we call this a quasar. And so we see these a lot in the centers of galaxies. And so I'm very interested in studying quasars in the very early universe. And so one great thing about these quasars is, as I keep saying, they're the brightest objects in the universe. It means that we can see them to extreme distances. So we can actually find quasars in the first billion years of the universe. And so we can actually measure those black holes and see those black holes right when they're starting to form. And so that's the really cool thing about quasars.
So this isn't my question, but it's a follow-on a bit from when you're talking about studying black holes and quasars. What sort of equipment are you using to study quasars?
Yeah, so generally I use optical or near-infrared telescopes. And so this is where the quasar is extremely bright. And so we can also see in those wavelengths the galaxy itself, so the stars in the galaxy. But you can also study, quasars emit across the spectrum, so you can see them from the radio all the way up to X-rays. And so basically, if there's a telescope, it could probably see a quasar. But yeah, I generally use things in the near infrared because I study the first quasars in the universe. And so their light, which was emitted in the rest frame UV and optical at those distances, is redshifted into the near infrared. And so to observe these very distant galaxies, we need telescopes that can see in the infrared. And so we've been using Hubble a lot to do this. And then now also we'll be using James Webb.
Shh, we're not allowed to talk about James Webb yet.
Sorry.
So when you look at these black holes, so one of the things about quasars is that when they were first discovered, they were mistaken for stars because they're really, really, really small. And so does a telescope like Hubble, which is above the atmosphere and has much better resolution, get you to that level, or are you still looking for more and more resolution?
So even with Hubble, always actually, these quasars will look like a star with a telescope. So the way that a telescope observes a single point of light on the sky, it's called the point spread function, or PSF. And basically that gives you the shape that the instrument will see as a star. And so if you've seen Hubble images before, you might see all of the stars kind of look a bit spiky. I think there are 4 spikes with Hubble. And other instruments that are coming in the future may have more spikes in there.
Secret instruments.
Other instruments may have different amount of spikes. And so see stars, they see stars all the same. They're a single point of light on the sky, but in the optics of the telescope and in the images that we get, we see them as a certain shape. And so this is true for any point of light that's what we call unresolved from the telescope. So stars are generally always unresolved. We just see a single point. And the quasars are very, very tiny. So they're right at the center of the galaxy. So they'll always be unresolved. And so they look like a single point of light. And so actually a lot of my job is focused on trying to determine this point spread function, or PSF, of the telescope. Because the great thing about quasars is they're very bright, but the very painful thing about quasars is that they're very bright. And so I want to see the galaxy that these quasars live in to try and understand where these supermassive black holes live and how do they grow. But the problem is I need to see the galaxy, but the quasar's in the way. And so at these distances, the galaxy becomes very, very small on the sky. And so it almost becomes the same size as a point source. We use fancy image analysis techniques to distinguish the quasar light from the galaxy light. And so we can kind of do that in the local universe pretty well. We can see underneath the light from the quasar. But as you go back and back in time, it actually becomes, at the moment, it's impossible. So for these first quasars that I study that are in the first billion years of the universe, we subtract off the light from the quasar and we can't see the galaxy. And so that's because of the limit of the resolution of a telescope we use, which is Hubble, which has the best resolution that we could get. And so to find the galaxies that these black holes live in, we really need a better telescope that can resolve those galaxies. So it just needs a much crisper image to be able to actually pick up the shape of the galaxy underneath that point source quasar.
We don't have that special telescope yet.
Who knows what it might be?
First rule of Telescope Club, we don't talk about James Webb Telescope.
I feel like almost every sentence I say involves Webb. So this is going to be a weird podcast.
It's okay. We're going to get
We'll
to
get
it.
there real soon.
We will get there. We promise
wait,
to spend
listeners.
about 4 hours talking about it. Now that we've got an understanding of quasars and how they work and how they are good for you to study, but also a pain in the backside, when you're looking at these quasars and black holes and the galaxies they live in, how do the black holes change the galaxies that they live in when you're looking at them further into the universe's past?
Yeah, so it's a really good question. Generally, in the
I wrote that
universe,
one.
I wanted to pretend I wrote it. I didn't write any of these questions, by the way. I'm often referred to as the 5-year-old drunk astronomer. So you have to talk to me as if I have no idea what you're talking about, because it's more than likely I don't. So,
am I speaking at an appropriate level for you today?
I'm getting the gist of it. So.
You let me know if you don't.
If I struggle, I'll put my hand up.
In the universe, there's a very kind of peculiar relation between galaxies and the supermassive black holes at their centers. So these black holes, they're very large. So they're between 1 million to 1 billion times the mass of our sun. So they're huge, enormous objects in terms of their mass. But compared to a galaxy, they're very, very small. Like they live right at the center of the galaxy. They affect the small number of stars immediately nearby in their orbit. But generally, they have no gravitational effect on the galaxy whatsoever. They're very, very small on the grand scheme of a galaxy. So somehow, though, there is a relationship between how big the galaxy is, so how massive the galaxy is, and how massive the black hole is, which suggests that they're related somehow, but it can't be. It's not gravitational. It's not having a physical effect in that sense. And so something must be happening for this to happen. And so there are a few theories about why these relationships exist. So they're called the black hole galaxy relations. One theory is that maybe it's just a coincidence that when galaxies grow, they grow when they have lots of cold gas, which can convert into stars. And black holes also grow by feeding on cold gas. So, if you've got cold gas, maybe you just grow both. Both of them are thought to grow via galaxy mergers. So if you have two galaxies colliding together, you will induce a burst of star formation, which grows your galaxy. Can also trigger a growth in your black hole. So you're growing both in that sense. But one other theory, and it's very promising, is that the black hole actually does have quite an impact on the galaxy. And so that's through something called Agn feedback. So these quasars are also known as active galactic nuclei, or AGN. They're active and they're at the galaxy nuclei and galaxy center. And so this extreme system of the black hole surrounded by its secretion disk is very, very energetic. And so what can happen is it can eject jets of energetic electrons from the center of the galaxy. It can also produce winds, which can blow out the gas that's in the galaxy. Sometimes it can either eject the gas or just warm up the gas. And so for the galaxy to form stars, the gas needs to be cold, and there needs to be gas in the galaxy in the first place. And so by ejecting the gas or making the gas hot, the galaxy can no longer form stars as efficiently as before. So this black hole actually can stop the stars in the galaxy from forming. So it's actually having some effect on the galaxy in that sense. So not only do they both grow together, potentially they have feedback with each other. So the black hole grows and it will actually stop the galaxy from growing.
That's actually pretty cool.
Yeah. So this tiny thing at the center can have a phenomenal impact on the galaxy itself. So these jets can extend like multiple times the size of the galaxy, if you've ever seen images of the radio lobes surrounding an active galaxy.
Hamburger Galaxy, well, the one we call Hamburger Galaxy in the southern hemisphere, it has those big, lovely big jets popping out from it.
Yeah. And so that's from just this little black hole at the center of the galaxy.
Yeah, that's amazing. I love it.
Yeah.
So it is a very destructive force then. It can literally just kill an entire galaxy off.
Yeah. Yeah.
Don't go near black holes, people.
For more reasons than that.
Yeah. Otherwise, you'll turn into our podcast and get spaghettified.
That's right.
So one thing I've just been thinking about is, so the secretion disk, like if we think of it on the scale of the solar system, like is it the same size or bigger? Or I've just done a very quick calculation from a paper. They've given 4.5 light days as a size of an accretion disk, which is about 780 astronomical units, which is, let's see,
similar to our solar system.
Yeah, I think about to where the.
I'll just let you guys discuss this.
So I actually saw some images of the two supermassive black holes that we have physically observed with the Event Horizon Telescope. So it's M87 and our own supermassive black hole. And so I saw those, so I saw those on to scale, and I believe the black hole shadow of our Sag star is about to the orbit of Mercury.
Yes.
Yeah. Yeah. And for M87, it was about to the orbit of Pluto. It was much larger. And so that's just the shadow of the black hole. Yeah. So I'm guessing the accretion disk is larger than that.
Yeah. So the Kuiper belt is about 50 AU away. So this is like, the accretion disk is much larger than our solar system, but, well inside a single light year. It's only about 0.1 light years. So it's not a very big, area to be making all of that light that you're seeing from them.
Yeah. And so these small disks outshine the entire galaxy. All of the stars in the galaxy just outshone by this one accretion disk.
Incredible. And I guess that relationship that we've just said about Sag star and M87 having different sized black holes at the center, supermassive black holes, and M87 is a much, much larger galaxy than our own Milky Way. And so M87 is an elliptical galaxy which has been built up through merging. So is there any ideas that maybe supermassive black holes also merge from when two smaller galaxies collide and their black holes merge, or is it more sort of organic in that they're just eating this gas and growing up that way?
Both. Absolutely both. So, definitely supermassive black holes are thought to merge with each other. And so one way that we hopefully will be able to detect that in the future is with LISA, which I've heard some of your guests talk quite a bit about before.
So can you tell us about the James Webb Space Telescope? What are you using it for?
So
where was the big intro?
We won the Webb.
Dun, dun. I was please tell us about the James Webb Space Telescope.
That's just how I am.
Pump it up, step in.
Pump it up. There we go. Pump it up enough.
What's your favorite thing about the James Webb Space Telescope?
Wow, what is my favorite thing about the James Webb Space Telescope?
All of it.
The fact that it's finally launched.
The mirrors are so pretty.
Yeah.
Can't get past those. They're really nice.
My favourite thing is that it finally got into space and works.
Yes.
Yeah.
You've been preparing for JWST for a while now. So what is your role in this sort of collaboration and effort in getting James Webb data out to the public?
Sure. So I've been involved in preparing for James Webb Science since 2017. So 5 years now. I've been waiting to see the data. And so I was involved through a team who have time on Webb to observe all sorts of things in the early universe. So searching for the first galaxies, looking at these high redshift quasars, and doing all sorts of exciting science. And because I was very involved with that and really excited by Webb, I actually put in a proposal to observe my own program and do my own science with Webb. And so the way that that works is it's a peer review process. So you submit a proposal and other scientists from around the world evaluate and rank all of the proposals. And it's very competitive. And so I was very lucky to be awarded time for my project. And so my project is to study 2 of these high redshift quasars that I was talking about before. And the key with Webb and what it can do better than Hubble is resolving these galaxies. So as I said before, the galaxy is hidden by the quasar. And to uncover that galaxy, we really need the galaxy to be resolved by a better telescope. And so Webb, because it's a much bigger telescope, so the diameter is about 6.5 meters compared to Hubble's 2.4. So it's a huge difference in the collecting area that it has. But that also is a huge difference in the image quality, in the resolution, we say, of the telescope. So the images are much clearer. And so that will make our galaxy become resolved, we hope. And so instead of seeing a single blob on the sky, it will be a bit of a bigger, nicer blob on the sky, which hopefully then we can actually see underneath this, because the quasar will always just be a point source. We'll actually be able to see that extended galaxy pop out of the image. And so, so my proposal, so I'm using Webb for 16 hours to study 2 of these quasars, which is super exciting. I'm very excited for that. And then now that I'm here in Canada, I'm also involved in the NearSpec team. So NearSpec is one of the instruments on Webb, and they have a really exciting science program studying lots of these high redshift quasars with spectroscopy, and specifically integral field spectroscopy. And so what that is instead of taking an image of your quasar, you're actually taking you're taking a spectrum of the quasar, but it's not even that. So you're taking an image of the quasar at every wavelength of light. So you could think of it a different way. You're taking a spectrum at each 2D spatial pixel. So you get a 3D cube of position and wavelength. And so basically what we can do then is not only detect the host galaxies, but actually find out heaps of information. So we can try and work out all sorts of stuff about the black hole. So measure the black hole masses really accurately. Also measure the star formation rates and masses and metallicities and all sorts of cool things about what these galaxies actually look like. We can also, as I mentioned before, that these quasars can blow out winds. And so using this technique, you can actually see if there are winds or outflows in the galaxy. And so, so I'm involved in a lot of different Webb projects, generally all studying the high redshift universe. And the ones I'm specifically very interested in and have a big role to play in is with the quasars themselves.
How exciting is it to be involved with James Webb?
It's super exciting. Yeah. So part of being involved in the NearSpec team meant that I was on the NearSpec science readiness team, which, so what's happened basically for the last 6 months is Webb was launched at Christmas and it traveled to its location at L2 and unfolded and became a telescope.
And got hit by some stuff.
And got hit by some meteorites. Mm-hmm. And so then once it became a telescope, then each of the instruments had to be commissioned, which involves testing them, basically making sure they all work as expected. And so because I was involved in that team, I got some early look at how the instrument was performing. So over the last couple of months, we've slowly seen a few little things come in about Webb and whether it's doing well or not well. Happy to report that generally it's doing really, really well, better than we all kind of had expected, which is great. So yeah, so it's been really exciting to be involved a little bit behind the scenes and seeing what actually happens when you build a telescope and commission a telescope. Because I have not had any idea. I just used the telescopes. I didn't know what was involved in that. So it's been really exciting to see that.
Yeah. So how many people are working on this process? You're doing one instrument, but Webb has many instruments, right?
Yeah. It's a great question. So I would guess, actually, there was a science paper released yesterday alongside all of the beautiful Webb images explaining the commissioning process and what we found. And the author list is around 500 people. So there are a lot of people involved, most of them much, much more strongly than me in making this telescope work. And that's just the commissioning side of things. So I've heard numbers of 20,000 people involved overall in designing, building, launching, science parts of Webb. It's a massive, massive community involved.
Yeah. So is NIRSpec, is that a Canadian instrument or is it a US sort of built instrument?
So NIRSpec is a European instrument, actually. So most of my collaborators are in the US. I don't know why I said the US. Most of my collaborators are in Europe. Yeah, so most of my collaborators are in Europe. But I also work with Canadians as well. So Canada does have an instrument on board Webb, which is NIRISS. So NIRISS is similar to NIRSpec. So NIRSpec is the near-infrared spectrograph. NIRISS is the near-infrared imager and slitless spectrometer.
Sorry, Steffi knows, and my son will hate me because I'm going to talk about him again on the podcast. But that's spectroscopy is what he's into. He's 15 and he loves it. And slitless is what he actually needs to use to. He's been trying to work out rotational velocity of galaxies, and the grading that he's got, he can't do it with. He needs a slitless one. And
tell him to use Webb.
I will. I'll tell him he's got to use Webb, and then he can get his little research project done.
Yeah.
I mean, Hubble may be an easier get at the moment.
Yeah.
So NIRISS can do both imaging and spectroscopy. And so it's really useful for studying exoplanets, actually, the atmospheres around other planets, but also for looking at galaxies in the distant universe as well. So there are lots. So there are 4 instruments on Webb: NIRCam, the near-infrared camera, NIRSpec and NIRISS, which I've just said, and then MIRI, which is the mid-infrared instrument. And so basically all of the instruments are capable of doing both imaging and spectroscopy in various forms. So there's lots of different ways to do things, lots of redundancies if something eventually breaks down the line.
Okay, now I have another question. So, okay, my first one was, so you use simulations of these black holes. So how does that connect in with using James Webb to take images?
Yeah, so for the last few years, we've been very heavily trying to investigate whether our observations of quasars will work with Webb. So obviously we didn't have Webb, and Hubble wasn't good enough for doing what we wanted to do.
Shame on you, Hubble. It's not good enough.
Boo!
I feel like Hubble's getting just like we've got James Webb now, and Hubble just wasn't good enough. There's a lot of that going around. Hubble's like the AEC's 25-inch telescope. It kind of just sits over to the side and gets pulled out occasionally when the 40-inch needs some maintenance done. It's like it's still there, and we will use you a little bit.
Yeah, Hubble is still very, very high in demand. I'm still trying to get time on Hubble, and I still get rejected.
Oh,
Boom!
Just a quick side note then. So if you got time on Hubble, what would you use that time on? Like, what would you do with it?
So what we really would like Hubble for is the coverage in the UV and optical, which James Webb doesn't have. So James Webb is not a replacement for Hubble. It's a successor in that it's built to do different things, but better than Hubble. And so it's a near-infrared, well, it's an infrared telescope because it's got both near and mid-infrared capabilities. Hubble could see from the UV all the way to the near-infrared. So there was overlap in the near-infrared with Hubble and Webb, but Webb can't see in the optical. And so the way we discover galaxies in the early universe is through the Lyman break technique. Now, Steffi is the expert on this, so I'm going to butcher this, and she's going to laugh at me.
No, that's okay. I'll be your
I won't
spotter.
laugh because I don't know what it is. So.
So basically what happens is because the galaxy's light has been redshifted from the rest frame UV and optical all the way into the near infrared, you see the galaxies, high redshift galaxies, they appear very red. And so you see them in very red filters. Do you want to take it from here, Steffi, in terms of why you don't see the galaxies?
Yeah, sure. So we have the universe is expanding, and as part of that, any light emitted from early galaxies is redshifted as it gets to us. So we have galaxies emitting at all sorts of different wavelengths, and one of the ones they emit at is ultraviolet wavelengths, and these come from the really hot young stars in these galaxies, which is great because we think that galaxies in the early universe, because they're really young, they're making lots of these hot young stars, so they have a lot of ultraviolet radiation. So the thing is, though, that the universe is also full of junk between us and these distant galaxies. So as the light goes from the distant galaxy to us, it passes through lots of hydrogen in galaxies, in just gas clouds in the universe, and then the hydrogen absorbs some of that ultraviolet light because hydrogen, it only has one electron and one proton, and that electron absorbs particular wavelengths of light. So the light that we see from the galaxy, it has some of the light missing that it originally emitted. And so we get these very clear spectral features. And so at this point, before James Webb, we couldn't actually really take spectra of the galaxies themselves. It was very, very difficult. It took days worth of just staring at the same little galaxy to try and get one emission line. But what you can do is you can use that lack of light, which is preferentially at the blue end, so anything that's in the ultraviolet or the optical, it gets absorbed by hydrogen. And so all you're left with is the redder light. So things that are redder and redder and redder, it gets more likely that they're further and further away. They could be other things that are between us and just look the same. And so up until James Webb again, this has been a really big issue with looking for galaxies in the early universe because there's lots of things that look like them, like stars that are, brown red dwarfs, galaxies that are closer to us but just have old red stars in them. But we have lots and lots of techniques that have been developed while we wait for GWST to try and tell them apart. So so that's basically how we find galaxies in the early universe. And so Maddie's quasars are a little bit different because quasar light is a bit different. And so again, they're also generally just brighter, so you can see them also out to very big distances. But I don't think you use Lyman break techniques to find quasars, is that right?
No, but what we actually want to use Hubble for is to study the environments of those quasars. So we're interested to know whether the quasars live in a kind of blank part of sky or if there's lots of galaxies nearby. And so to do that with Webb, we can measure very accurately all of the near-infrared filters to see, okay, these galaxies, there are things here that are quite red, but you need the blue filters, so from Hubble, to actually say, okay, this is a high redshift galaxy or, it's just a nearby galaxy. And so you really need those images in the optical to do that technique. And so what I keep asking Hubble to please give me is observations in the blue of our two quasars. So to try and see, so when we have our Webb data, we can actually try and work out if there are high redshift galaxies nearby our high redshift quasars. So Hubble is definitely hasn't gone out of style. Everyone still wants to use Hubble. I'd argue cool. Maybe even more so because we've got all this awesome web science and we need definitely. Hubble to do supplementary things.
Yeah.
Yeah, it's not. It
So
hasn't. People haven't
Hubbles like
lost
the
interest.
Tony Hawk of the of skating. It's still cool.
So cool. Getting on a bit, but
Getting on a bit, but still cool.
Exactly.
yeah.
Yeah. So the teams that I'm involved in are doing a lot of work on the clusters, and there are a lot of people around the world right now scrambling to do as much science as possible.
Yeah.
And I am willing to guarantee that by the time this podcast airs to the world, there will be scientific papers out in the public
Absolutely.
on these
Yes.
first Webb images.
Yeah.
They better get going quickly because I'm going to get this one done today.
Yes, well, from what I
bet,
understand, there will be papers submitted tomorrow.
Yeah.
Wow.
Yeah,
Okay,
because
that's
probably what they've
pretty
been
impressive.
doing, Mark, is that they've got the paper already written.
Yeah.
The FITS files, so the sort of FITS files are the standard way that we manipulate sort of astronomical images, were released this morning, I think, or overnight here in Australia. So,
Oh,
yeah. So they were released this morning. So what they would have done is had their paper already written, taken the data, had, a few hours to look at the data, and then plug that into the paper and submit it. And when you do things like with transients, so Sarah Webb probably is familiar with this sort of thing, but if you've got a transient and you've only got a certain amount of time to look at this thing before it disappears, you have to be ready to just work quickly. And so I think this is another of those sort of times when it's like, we've had 4 years or whatever to prepare for. We know that the ERS, the science program, was released in 2017. So you know that these are things that are going to be looked at. So yeah, that doesn't surprise me, Maddie, that people are preparing already to put their papers out.
But I love that. So we're doing this on the 14th of July, and then we're saying that. So James Webb released its first image on the 12th of July, 2 days ago.
Yes.
Yeah.
Well,
11th in North America.
we don't. No, it's all about Australia. So we'll say it's the 12th of July in Australia. The first images were released. We're interviewing you on the 14th of July. This will be out hopefully tonight, if not on the 15th of July. And then in that same day, in that same small window, papers are going to be released. And that's just, I know you're saying it's all ready to rocking to go, but it's just so cool that it happens, or it feels like it happens so quickly.
Yeah. So as Steffi said, we've known for a long time what targets will be observed, and everyone's kind of prepared for those. But the really interesting thing about the 5 targets and images that were released this week were that no one knew what they were. So we didn't know until last week what those targets were. So the way that it worked is astronomers around the world involved in Webb came up with a massive list of really exciting things to observe. And I think the list was about 70 objects long. And so they went through and came up with the best targets that would advertise the capabilities of Webb and the different science instruments and what they can do, and basically images, coming up with things that would give beautiful images. And so it was narrowed down to the 5, but it was a very well kept secret. There were a lot of people very highly involved in Webb that didn't know what they were.
Wow.
And so they released these targets on, I think it was Thursday last week. And since then, everyone's been scrambling. They're like, right, we've got this cluster coming. We weren't prepared. We were prepared for our cluster observations, which we've known for years. But this one was a surprise. And so people have been scrambling to get models for how the lensing system works. And then so yesterday, the PNG images were released. So just the images, no science data at all. And so people were starting to do science just on those, like, okay, this is what we're actually going to see when we get our proper FITS images. Where are the things that we care about? What's interesting? What's going on? Starting to write the papers. And then this morning here in Canada, so it was about, this morning our time, the actual science data got released. And so the floodgates opened and everyone's scrambling.
So I love it. I absolutely love it. It's so cool.
Today, only the science data for those 5 targets was released. Tomorrow, things will get even more crazy because all of the data taken to by Webb up until this point will be released.
Yeah.
So all of the
Okay.
commissioning data, so there's
Yeah.
40 terabytes worth of commissioning data, and all of the science data. So Webb's actually been taking science data for quite a few weeks now. And so our team has 3 different targets that have been observed in the last couple of weeks. But none of that data could be released until all of this exciting stuff happened yesterday. And so now tomorrow we actually get our targets. And so we're already crazy busy and excited with this cluster, and now we're going to have just so much more data. And so there's a lot more public data coming.
I was just about to ask that. All that data that's coming, is that all going to be publicly accessible, or only some of it?
Only some of it. So there are the early release science programs, and there's from scientists around the world who basically propose to do science, but as a community tool. We're doing it for us as a whole to understand something about the universe or to understand how Webb works. And so that data all becomes public as soon as it's taken.
Yep.
And so there are some deep fields. There's a cluster. I'm sure there's lots of stuff in the local universe, but I don't pay attention to anything very close by. And so that will all be public immediately. But then also, so people like me who have requested time, that is always private for a year. So we have a year to do science before it can be scooped by anybody else. So we don't have to rush quite as hectic. Whereas these clusters that came out, this cluster that came out this week, everyone has access to the data. And so everyone's doing the same thing at the same time. And so it's pretty crazy.
It's amazing. It's so cool. So much excitement. The next one, which kind of leads on to all of this data and this access to images, is your favourite newly released image. I have a favourite and I have a reason why, but I'll wait for you to explain yours.
Oh, I hope Steffi has a favourite too, and we can see if we were all the same. I can guess which one Steffi's favourite would be. My favourite, in terms of how pretty the image looks, I think the Southern Ring Nebula. It's beautiful. It's got absolutely nothing to do with my science. I can't get any science out of it whatsoever, but I just want to look at that all day. Beautiful. Same with the Carina Nebula. That's just phenomenally beautiful. But my favorite would have to be Stephan's quintet.
Yep.
So there are 4 interacting galaxies plus 1 galaxy that's just hanging around in the foreground that isn't actually anything to do with them. And when you look in the mid-infrared, you can see very clearly this beautiful shining quasar. And I was so excited to see that. I didn't expect that we would see a quasar for our first images, but there was one. And so not only did we get images of Stephan's quintet and that supermassive black hole at the center of one of the galaxies, they actually took spectra. So they took this IFU spectra that I was talking about that I'm going to be using. They did that, plus they did the same thing with MIRI and took spatially resolved spectra of that supermassive black hole. So that will be exciting to see what science comes out of that as well. So NASA released very small images. You could just see a little bit of what that spectra looked like, but it'd be interesting to see the scientific analysis of those. But the Stephan's quintet was just beautiful. So it's these interacting galaxies. You can see a gas stream between the two where they're pushing each other, and you can see that black hole. It's beautiful. I mean, they all are. It's very hard to pick.
Steffi, what's your favourite?
Mine is, I think Maddie's expecting me to say the deep field, but I have a slightly well-known bias against lensing images because, as we mentioned, they are a pain. Mine is actually the exoplanet transmission spectrum. I think that is amazing. So the way that the way that it's taken is you're staring at a star, and usually you do this with. Sorry, I have my hands in front of the microphone. Good job. You take imaging, and so this is what Kepler did. It stared at a patch of stars in the Milky Way for a long time, and every so often you see blips where the light is reduced as a planet goes past. And so what people have been wanting to do is And I think there's been some success with this before JWST, but it's tricky because you want to look at the atmosphere by looking at the light from the star that is absorbed by the planet's atmosphere. So any light that doesn't make it through the planet's atmosphere, basically. And so JWST, because it's so big and has such great resolution, and it has these amazing instruments like NIRISS, can actually take a spectrum of a planet. And so what they've said is that this spectrum that they've put out is not super well, calibrated or anything yet, but you can see plenty of water features, which is amazing, because this is a really hot gas giant planet, which is really close into its sun. So water there is not something that is going to indicate life is there, because it's a gas giant and it's hot. But it's just that, water is actually probably ubiquitous in the universe, where we thought it was really rare. So I think that's awesome. Infrared is great for water because, as we know, water absorbs a lot of infrared light, which is why we can't see any infrared light from the ground. We need space telescopes to look at it. So yeah, I'm just amazed at the thought that we can see this tiny, tiny little signal as this planet passes in front of the star and see what's actually on that planet's atmosphere is, I think, amazing.
Yeah, that one's really cool. So one of the hopes for Webb is that because we're looking at the infrared wavelengths, some of the key molecules in atmospheres that may point to signs of life are oxygen and methane. And so particularly methane, a lot of science is supposed to be done with Webb. And so it'll be really interesting to see what we find about planets over the next year or so, because there are a lot of planets being observed with Webb because of the capabilities to see what are they made from. So that one's really cool scientifically. I agree.
Yeah. It's
not as pretty to look at, but
a bunch of dots on a plot. But I think it's awesome. In terms of prettiness, I think it's a toss up between the rest of them, honestly.
It's so hard to pick.
I don't want to choose. I made you choose, but I don't want to.
Well, mine, I've chosen the one I chose is purely because I feel like there's a hidden message in it, and that's the Carina Nebula one, because it's the portion of sky that's actually NGC 3324, which is otherwise known as the Gabriella Mistral Nebula. And anyone who knows anything about Gabriella Mistral is that she was an educator and a humanist. So I kind of feel like it was NASA and ESA's way of saying, we're going to educate you. Probably not, but I just love that little link that they've imaged this part of the sky that is named after somebody who was all about education. And it's gorgeous. It looks beautiful.
Yeah, really cool. I hope that's the real reason, because that's a beautiful
reason.
Probably
not, but it's a cool idea to think that it might be the reason.
Yeah, it's really nice.
My favorite part of that image is that the James Webb image that is released is just such a tiny little part of that overall cluster. And even in that tiny part, we see so much detail. And you can compare the HST and the JWST images and just see that JWST gives you so many more stars peeking through all that gas, which is what happens when you look in the infrared, but it's really cool.
There's just so much depth. It really looks like a 3D thing, as opposed to really with Hubble, it looked like a sheet of dust and then you just stop there. But with Webb, you can start to peer through the gas and it comes out as this beautiful 3D structure.
Yeah, you feel like you can reach over and just peel it back.
Yeah.
So there's an astrophotographer, Andy's Astro, and he has imaged that area quite a lot. And I'm actually going to ask him if I can put his image up on this when we put it on YouTube. And he's actually located where that section is on his image, and just to show the scale, the difference. So from the entire region to what little part they imaged for that gives a very good scale of how big things are actually out there.
Let's move on to our final question for you, Maddie, which is, what are some things you like to do when you're not doing astrophysics?
So at the moment, it's summertime here in Canada, and in Victoria, which is where I live, we're surrounded by nature. It's absolutely beautiful. So we're going on lots of hikes and kayaking on the weekends. Canada has a massive canoe culture, so it's nice to be on the water with everybody else. But generally, I really like to bake. and craft. You name it, I've crafted it. So Steffi and I have this in common.
Yes, Maddie has a video on YouTube about making galaxy cupcakes, is it?
Yeah, that's it.
Yeah.
I explained my research while making cupcakes.
All right. Yeah. I'm going to show my daughter that. She will absolutely love it.
That's good. When I said that I was coming on a podcast with Steffi, my partner Oliver said, "So is it a podcast about science or are you just going to talk about knitting?" And I said, well, we could do either. So he'll be pleased we've, included the knitting.
All right. Do you want to introduce the last part, Mark?
Oh, yes. Spot quiz.
I haven't told her about this.
Haven't told her about our spot quiz.
I have been listening to the show, so I know what's coming. I'm not excited about it. But...
I'm very excited. I wrote these questions. Usually Mark writes them. Maddie knows that I am a trivia fiend, so I was very excited to write these questions.
No. Oh, no, Steffi.
So we do our spot quiz. Obviously, it's on the first letter of your first name. Mm-hmm. So yours is M. Mm-hmm. And Steffi has selected maple syrup.
Oh my goodness. I am so nervous because all of my Canada cred could go down the drain right now. Now, speaking of going down the drain, I have a maple syrup story. Now,
okay, yes.
I don't know if you knew, but maple syrup goes off.
Oh, no.
I didn't know that was a thing. I would always just, I have a lot of maple syrup. And I was baking not long ago. I'd made these. They were supposed to be maple cookies. And it was the last step. I just had to pour a little bit of maple syrup in. And I poured a little bit of maple syrup in. And it was just weird looking. And I thought, I'll just put a bit more. And then I looked and I was like, that's not right. It looked like there was cocoa sprinkled on top of my maple syrup. And I Googled it and it's mold. So I had to pour my whole bottle of like $20 maple syrup down the drain.
No. Oh. Well, our podcast is now public service.
Buy moldy maple syrup, but it is one of my favorite things to eat. So I'm hoping that gives me an advantage today.
Hopefully.
So public service announcement, maple syrup does go off.
Yeah, look out. Be aware. You're actually supposed to keep it in the fridge, and so I do that from now on. Yeah.
I see. I never have because I love it when it's runny.
So it doesn't go hard. It's just,
I'm going to make sure my Canadian maple syrup just in the pantry gets put in the fridge.
Yeah, as soon as it's open, pop it in the fridge because I've learned, I mean, luckily I didn't eat anything, so I can't say I learned the hard way, but I learned the kind of hard way.
The sad way.
All right, question 1. Which Canadian province produces the most amount of maple syrup?
Okay, so I'm in BC. We do not produce maple syrup, really. It's definitely on the West Coast. I know that they have a lot in Ontario and Quebec. The other provinces are too small, so they probably produce a lot, but I think based on land mass, I don't think they could produce as much as either Quebec or Ontario. So based on that logic, I've narrowed it to 2.
Someone's taking this very seriously.
I am not surprised at all by this. I will tell you as well, Maddie. Sarah Webb actually get 4 out of 5 questions.
Oh, I definitely can't do that. But I just want to, okay, so it's Ontario or Quebec. I'm going to go Ontario.
Thumbs down. Should have gone Quebec. It produces 70% of the world's maple syrup.
I was close. I was close, wasn't I?
You were. It actually produces 90% of Canada's maple syrup, which I think is amazing.
That's a lot of maple syrup.
That's a lot of maple syrup. My question is, how many liters of maple sap are needed to make 1 liter of maple syrup? There is a range here, so we'll take,
Okay, maple sap to maple syrup. Are we going order of magnitude? Well, that's too wide of a range. That's fine.
Slightly too wide, yeah.
Okay. I've seen it done, not in person, like the whole tapping a tree process. Mm-hmm. I don't reckon there's heaps lost. I'm going to say 5 times as much sap to syrup. Yep.
I mean, order of magnitude, that is correct. It's actually between 20 to 50 litres. So,
wow, that's a lot.
Yeah, so the average maple tree will produce 30 to 50 litres of sap per season. So about a litre of maple syrup.
Wow. Wow, that's not much.
Yeah, because it's
That's why
a lot
it's so
of
expensive.
water.
Yeah. It's
So
bizarrely,
do we
it's
give
more
it-
expensive here in Canada than it is in
Is it?
Australia. And I do not understand how that works.
Is that because you have a
Yeah,
different
that's
grading
odd.
system?
Well, interestingly, so yeah, at home we just buy maple syrup, right? So in our supermarket, there are like 5 options of grade A, grade B, dark robust. Like, what kind of maple syrup do you want? I don't know.
One of each, please.
I'd like to do a maple syrup tasting. But
you
yeah.
can do that apparently. It's similar to wine tasting.
Yeah.
I learned this as I was researching maple syrup last night.
I would really like to go to, as I've now learned, Quebec, to go to a maple farm. But I just knew that, yeah, you can't do it here. So unfortunately.
Maple under the stars. That's another event.
That'd be awesome.
Okay, so I'm doing really poorly. I've got to get one right, or my Canadians are going to really hate me.
Losing your cred. So, question 3. Do you get more sap from trees in warmer or cooler climates?
Let's say warmer.
Oh, not doing very well on this one. Another thumbs down. Cooler climates. Cooler climates, the sugar maple requires cold temperatures to grow, and seeds cannot germinate in temperatures above 10 degrees.
Above 10.
Celsius.
Interesting.
Yeah, so I think that's why it's because you start sort of Vermont, Maine-ish sort of US, and then go up into Ontario and Quebec. And so yeah, apparently the ones further north are you get more sap.
Better, 'cause it's colder. Interesting. Yeah.
It's such a weird tree, apparently.
Yeah. I was thinking like we don't get maple syrup if you go higher in Canada, but I guess it's probably because we don't have trees.
And so apparently it's one of the only trees that requires like frost to actually have part of its life cycle.
Okay.
Yeah. Question 4. What methods did Indigenous people use to turn the sap into syrup?
I've been to some really Indigenous museums, but
Yeah.
they're all in BC where we don't have maple.
Should have asked you about what's a canoe word that starts with M?
Moose.
Well, moose was the other option I had.
The Mounties. Okay, so the question was...
do you want me to repeat it?
Give me a hint about what the question actually was.
Yes. So, what methods...
the methods for the Indigenous people. Yeah.
Yes.
Okay, so I'm guessing you have to make the maple syrup hot to turn it to sap. I don't know.
On the right path. Can we say on the right path?
Yeah.
On the right path.
I think fire is too obvious. So I don't know. Maybe they dig a hole because I think you tap your maples at the end of summer, like close to fall. So it's starting to get pretty cold. So the ground might be warmer. So I don't know. I'm going to say you put it in the ground.
I am going to give you half a mark for that if you're okay, Mark, because you got sort of halfway there on both fronts. So along with boiling the sap in clay pots, they would leave it to freeze overnight and then discard the ice that formed on top, reducing the water content. So
interesting.
Yeah. It's like, and then apparently children could also be given this ice with a bit of maple stuff on it to eat as a treat.
Well, there you go. Yeah.
Kind of like snow cones.
Yeah.
Maple syrup flavored snow cones. I'm up for that.
Yeah. I think they have maple toffee, which is just, keep reducing it and it's like a sugar. And
that would be so yum.
They don't have it here that I've found. But see, I'm living in the wrong side of Canada. Not where the maple syrup's at.
Go and get a new job. New
job in Toronto. Or
No, because that's in Ontario, Steffi.
I know, but it's close enough.
We've learnt the Quebec.
Last question, and then I'm going to go and buy pancakes and have maple syrup with them.
Good point.
Why do maple syrup bottles have those teeny tiny handles?
It's bizarre because like here you can get it in a plastic bottle or a glass bottle and they both have the little tiny handle.
Canadians are weird.
For aeration? Obviously not, because that's stunned silence if I've ever heard it.
Sorry, no, I just forgot if I was answering or if
we'll give you another go at answering that.
It was that bad of an answer that they're letting me go again.
I was waiting for more. We'll go that long.
Well, I don't think I should elaborate because I think it was clearly the wrong answer. tell you my logic.
So they used to be put in stoneware jugs, and the jugs in the 1800s, and the jugs would have those little handles on them. All stoneware jugs have those little handles.
But the handles in that point were actually functional because jugs were
right.
bigger.
Certainly not functional. Well,
and then they switched to smaller glass bottles, and they kept the handle out of nostalgia. And they just kept the handle in proportion to the bottle size.
Well, there you go. So I guess that means we used to have massive bottles of maple syrup.
Yeah,
that's the way.
Flagons of them, like big.
I told you yesterday, Mark, that I had one more question to write, and that was the one I was just like, I need to find the answer to this. Why do they have tiny handles?
I love it. It's so
that's so good, and I'm so ashamed.
No, right.
I haven't got Canadian citizenship yet, and after this, I'm never going to get it. I'm now ruled ineligible.
Yeah.
We'll make sure that's announced loudly and clearly in the podcast release. Do not give Maddie Canadian citizenship.
I don't deserve it. In my defense, as I've said many times, we don't make maple syrup on this side of Canada. Yeah. And Canada, like Australia, is a very, very large country. So,
do you think you would have done better if we'd asked you about moose facts?
Look, it depends on the facts, doesn't it?
You could have thrown Rocky and Bullwinkle questions in there.
I'm generally atrocious at trivia. I know I have lots of random information in my head, but nothing useful in terms of either actual use or trivia use. It's just kind of like fluffy information, if that makes sense. So like I consume a lot of fact podcasts and videos and stuff. And at the time I'm like, wow, that's really cool. And then I'll be like, yeah, I learned this cool fact about, fish today. Can't tell you what kind of fish because that's gone.
I don't think you'll ever forget about the handles question now.
No. Might go and have some maple syrup to feel sorry for myself after that terrible performance.
Thank you so much for joining us, Maddie. I think that was an amazing chat about James Webb and all of the amazing things that you personally are going to use it for, but then also everyone around the world has been planning on using it for. We'll get some more results over the next week or so, and then as more and more data is released, I'm looking forward to seeing everything else that it makes. So hopefully we'll have you back at some point to talk about your discoveries with it. Thanks so much again, and thanks for listening to Spaghettification. Bye, everyone.
Bye.
See you later. Thanks for listening and supporting us as we continue to learn on our podcast journey. If you would like to contribute to the podcast, you can head to www.patreon.com/Spaghettification podcast and support us for as little as 1 can of beer a day.